All right, good evening, everyone. I'm here to talk to you tonight about the ZIO2 runtime system. And in particular, I'm going to talk about improvements that are scheduled to land in ZIO 2.1. I'm going to first give you a little bit of background on what's all the fuss about a runtime system. What is a runtime system and why do we care? And where is ZIO's runtime system and where does it come from? And then I'm going to spend the bulk of this talk on giving you some insight into some recent work that I have been engaging in over the past few months, bringing Loom support to ZIO. And I'll give you just enough background on Loom so if you've never heard that word before, you at least know where I'm coming from. And then I'll review a series of recommendations that I'm going to give to every ZIO user out there who wants to make their code as Loom ready as possible. If you want to get the most from Loom, then you need to take very specific steps in your applications, and I'll tell you what those are. And then finally, I'm going to end by giving you a sneak peek at some of the upcoming work that I'm scheduling into the ZIO 2 runtime system. So a runtime system, RTS for short, is basically the engine of the ZIO library. When you build an application using ZIO, you're building it using something called an effect. And an effect is basically like a workflow that describes a series of steps, some of which are sequential, some of which are parallel, as well as maybe resource allocation and concurrent state modification, maybe context propagation, and maybe errors. So that's what these workflows describe, is this complex series of steps that has to be orchestrated. The orchestration process itself takes place in the runtime system. The runtime system is responsible for taking a ZIO effect and executing it from A to B, producing the final result, or maybe failing along the way. The runtime system is extremely complex in any modern effect system. It used to be you could write a toy runtime system in probably around 20 lines of code. But over time, Scala's effect systems have become increasingly sophisticated. And the level of power that you get with these effect systems, I think you could see that in that last presentation where you gave you the example of retry and ignore logged and all this stuff, just chaining all this stuff together and getting something that's bulletproof and resilient and invincible and flexible and whatnot, concurrent, out of just a few lines of code. Well, that requires some pretty hefty guarantees, and it's the job of that runtime system to make sure that those guarantees are upheld. So ZIO 2 featured a completely new runtime system. Pros and cons of that, I'm not going to go into depth on that tonight, but I did a very, very lengthy blog post on the new runtime system at dgoes.net if you want to take a look. Brand new. Shares zero code with the runtime system of ZIO 1. And it shipped 10 months ago. So it's relatively new in the grand scheme of things. It takes actually a few years for a runtime system to go from the first time it breathes life to a point where it's very mature and solid and basically can't be improved anymore. And ZIO 2's runtime system is very, very early. And it actually featured the first so-called third generation design of any effect system. The first time someone went to write an effect system in Scala, it didn't work out so well. They wrote it and found that basically after a certain point in time, their program would always Stack Overflow exception. And that's because of basically the way Scala is translated to the JVM means that you can only have a finite chain of stack frames before you run out of memory. It's not a necessary limitation, it just happens to be the way the JVM works. And as a result, the early effect systems that were created, they Stack Overflowed. And fortunately, at some point, I can't remember who is the original author of this technique, but it's a technique called trampolining, which allows you to, instead of storing information about what to do next on the JVM stack, you store it in the JVM heap. And heaps can grow without bound. So they can allow you to write very, very long programs without stack overflowing exception. This technique called trampolining was first utilized in Gen 1 effect systems like Monix and Scala Z task. And later on, streams, I can't remember, functional streams for Scala that had a name before that. Scala Z stream, that's what it was. It had its own effect type at one point, and that used a trampoline as well. These trampolines were the birth of modern Scala effect systems because they enabled you to write programs of any length, even recursive programs, programs that recurse forever, even programs that are mutually recursive and never end. You can do all that stuff in constant amount of stack space. And you just trade off using heap. Sort of, you end up using heap for that, and heap can grow up to 2 gigs and shrink back down to 2 kilobytes. So that was the entryway into the world of functional effect systems. And then things took a major leap forward with Gen 2 effect system. ZIO was the first Gen 2 effect system that tries to bake concurrency into the effect type. It was very controversial at the time. People were saying, no, you shouldn't do that. And even if you could do that, it wouldn't work. Well, obviously, you know, years later, it's the way that all effect systems work these days. They bake in this notion of a fiber. And they say, well, you fork or you start an effect in the background and you have something that's running. We call that thing that's running a fiber, and you can either interrupt it or you can join it. So that fork join concurrency is the basis for all Gen 2 effect systems. And it was a major, major, major breakthrough because up until that point in time, if you needed concurrency in the world of Scala, you had to go to a streaming library. That's it. I mean, you could go to the reactive solutions. The reactive solutions, observables and all that stuff, they had their own mechanism of concurrency. But if you wanted concurrency on the sort of functional side of the Scala fence, then you had to get it from a streaming library. And fibers, and you can't introduce fibers without solving the resource problem, but they're closely connected. You need some sort of primitive like try finally inside an effect system. So once you have that and you have this notion of fibers, you can build massive amounts of concurrency machinery on top of those primitives. And in fact, in ZIO and Cat's effect and Monix and any other future effect systems, all of their concurrent machinery is going to be built on that notion of something that's launched on the side and running independently that we call a fiber, might be called a virtual thread at some point in the future. Third generation effect systems. So first generation effect systems are all about not executing code on the JVM stack and moving that to the JVM heap. And that's so we can solve stack overflow exceptions. Third generation effect systems reevaluate that decision. And they say, well, if you look at it, in an average program, there's an awful lot of code you can execute on the JVM stack without throwing a stack overflow exception. So why not try to execute it on the JVM stack? And if you can't, you can always fall back to heap. This technique allows you to achieve the superior performance characteristics of executing your code on the stack, because a heap is way slower than stack. Okay, so you achieve superior performance characteristics executing your code on the stack while not sacrificing the beneficial effects of a trampoline. Basically, you pay for the trampoline only when you need it. And ZIO is the first and currently the only effect system that is third gen. This third gen effect system, I think, builds on a long history of innovation in ZIO, including ZIO being the first to really get concurrent computation right, introducing fiber-based concurrency with fork join semantics, being the first to introduce structured concurrency, and not just structured concurrency with sort of first-class scopes and all that stuff, but auto-supervision. Basically, most ZIO programmers who use fibers don't need to worry about terminating those fibers because ZIO is the only effect system that terminates them automatically when their parent ends life. Interruption, ZIO introduced fine-grained interruption, very controversial at the time, but basically now we all take for granted, no matter what effect system we use, we take for granted the fact that we can interrupt something no matter where it is. And that was very controversial. The early days, the early effect systems, you could never interrupt them, ever. They would run to completion, like Future, right? And then ZIO said, well, let's, then like sort of in between V1 and V2, they said, well, let's introduce a little point for you to do interruption. Like you could have an operation that says, interrupt me here if the result is not desired, right? And that didn't live very long because ZIO introduced auto interruption, which is you can interrupt anything anywhere for any reason and you can't stop it unless you wrap it in a block that says don't interrupt anything inside here. ZIO also made controversial decision to make all interruption back pressured. That means you try to interrupt something and you won't continue until that thing is actually interrupted. That has numerous implications, like you race two things, the race doesn't succeed until the loser was interrupted. You time out something, the timeout doesn't continue until after that effect has succeeded in timing out and being wound down and all resources associated cleaned up. That makes ZIO super safe by default. Without back pressured interruption and simultaneously with the ability to create massive numbers of running fibers, it's very easy to create or lead into a situation where you have a resource leak that's hard to diagnose. But if you back pressure everything all the time by default, you never leak anything. And just occasionally a programmer might say, why is this taking longer than it should be? And so you'll have to diagnose that and say, oh, well, it's because we're waiting on that thing to clean up. And if that's not the right choice, you can always fork that clean up into the background. You have an operation called disconnect that lets you basically push back pressure into the background so it's not going to interfere with the foreground. And that lets you get the semantic you want. Safe by default, but when you really need the sort of risky ability to do something in the background and not wait for that cleanup to happen, you can do that with disconnect. We innovated with observability. We did async stack traces first, fiber dumps, and metrics. Resource safety. We were the first to launch concurrent resource safety and the only effect system right now that unifies ordinary effects with resourceful effects. Right? There's no separate Z managed or resource or whatever that has duplicate implementations of all these parallel operators and whatnot. We used to have that in ZIO 1, but now in ZIO 2 we just have ZIO. And ZIO itself is sufficiently powerful to describe the distinction between an effect that does not need resources and an effect that does need resources. So you get all the benefits of that, but without any added overhead or duplicate implementation, which means you can have more confidence in the performance as well as the correctness of the implementation. ZIO has typed errors, and it's the only mainstream effect system to have typed errors. Also, loss-free error model. You never lose errors with ZIO. Sequential errors, parallel errors, defects, all interruption, all of that stuff, you can gain access to that. And all that is piped into ZIO logging and whatnot, so you never lose errors. We have really strong, and we were first with software transactional memory to eliminate races and deadlocks in your applications. Also, we have novel patch semantics for fiber ref. So basically take a thread local and fix all of the problems with it and bring it up to date with virtual threads, and you get something that's akin to ZIO's fiber ref. Fiber refs have very precise semantics. They actually preserve maximal information. As you fork fibers and later join them, the information that they accumulate in their own fiber refs gets merged into the parent fiber. And that gives you the ability to do concurrent state in a principled way that doesn't leak information, leak or lose information. And the absence of those semantics actually causes a lot of pain with thread locals and other like IO local and whatnot. ZIO gives you, as you've heard 2 talks today on the topic, the ability to create large-scale structured applications. So modular applications using compile time dependency injection. And that's just operations, right? So we were the first to introduce config and logging and metrics into core with this batteries included philosophy that you shouldn't have to do anything. All the library ecosystem should give you a ton of stuff out of the box for free, and it should be very, very easy. Getting config back should be as easy as calling zio.config. Logging should be as easy as calling zio.log. You shouldn't have to do more than that when you're building an app to get all of these rich features out of the box. So, not all is rainbows and sunshine, however. A new, brand new runtime system in ZIO 2.0 led to total wholesale replacement of lots of code. And also we introduced some more features such as auto blocking, and we had a few kinks along the way. We had some hiccups with auto blocking, occasionally detecting blocking threads that weren't really blocking for a sufficient long period of time. Basically, if you enter a synchronized block, like if you use a synchronized collection or something like that, technically that could be detected as blocking. So spurious detection of blocking, some of the auto blocking stuff. The concurrent weak set for fiber roots was not garbage collecting frequently enough, and that was leading to retaining in-memory fibers and all of the information that they were capturing over. The config thing was immature. It missed a lot of core operations and whatnot when we shipped it that had to be, we later discovered and had to fix that stuff. And then various little bugs and missing features here and there we discovered over the course of, I'd say probably the first 3 or 4 months of having that new engine out there in the wild. The good news, though, is that ZIO 2.0 is rock solid now. I mean, as of today, it is extremely solid. And it's so solid that I had to go back and fix some of the tests because we were actually, with the way the new runtime system works, it introduces more concurrency than ever before into your application. And that helps you identify tests that were like almost correct, 99.9% correct, but they weren't quite correct. There was always a chance they would fail when they shouldn't. And so it resulted in me and Adam having to go in and fix a lot of these tests. And that's a good sign. When your runtime system is so solid that it forces you to fix tests that you previously thought were correct, that's a pretty good sign. So the ZIO 2.0 runtime system is deployed in production at lots of big companies, and it is handling massive loads. That's not to say we can't do better. We will improve it, and part of my talk today is about improving it, but it's in a really, really good position for building production-grade applications. In this world, we have recently seen the launch of Project Loom. And Project Loom is doing something quite new and remarkable. It's trying to solve one of the biggest pain points in most modern back-end programming languages. Pain points, by the way, that not even Rust has solved. Okay, new language like Rust has not solved this problem. Well, the JVM is solving it, and it's solving it in exactly the right way. What this problem is the fact that operating system threads don't scale very well. And to solve it, Oracle said, well, let's implement our own thread, a green thread, and we'll have a sort of many-to-one mapping from a green thread, a virtual thread, Loom calls them, to an operating system thread. And as a result, they are able to make threads, at least virtual threads, scale extraordinarily well. Gone are the days when your application can only have 1,000 threads at most. With Loom, you can have 100,000 threads, maybe even 1 million threads. And they're so cheap, so low cost, you can use them whenever you want, for whatever reason. They're like ZIO's fibers, in fact. In a nutshell, they give you super cheap and scalable threads. And all your blocking code before Loom becomes magically non-blocking. So all the nasty code we used to write 15 years ago that blocked threads and slowed our applications down before we discovered the light and started writing reactive style applications, that all is now magically async, magically non-blocking, in the sense it doesn't block operating system threads. A virtual thread blocks, but that's like a fiber blocking. It's super cheap. And with the arrival of Loom on the scene, it is now time to kiss goodbye to reactive programming. It's gone. Bye-bye, reactive programming. It was nice knowing you. All the async frameworks and the observables and the and-thens and the weird DSLs we created to encapsulate the problem that threads don't scale, all of that's gone because now threads scale. Before Loom, this was the worst possible code you could write if you were interested in highly scalable concurrent systems. Right? The thread sleep is going to block. That's an operating system level thread that's blocking. Input stream read? No, never. Because read, it could return in 2 seconds or it could return in 2 minutes, and that operating system level thread will be parked and all of its allocated memory and other resources will continue to be used. Now, this is horrible, nasty, awful code that led to the creation of reactive programming, more or less. And today, this is best practice code. You can't do better than that. This is the code that everyone should be writing. In fact, if you're writing the old callback style, that's the legacy, nasty, awful stuff that you have to go back and scrub from your aging code bases. But that's not to say that in a post-LOOM world, effect systems like ZIO have no place. I'm not going to go into all the reasons you might want to use an effect system like ZIO 2, because I already gave a talk about that at Functional Scala that's online. Please check that out if you're interested in a detailed argument for why effect systems still bring a lot more to the table than just virtual threads. But briefly, you get things like compositional concurrency, error management, eliminating races and deadlocks, structured concurrency, all this really amazing stuff you get out of the box with an effect system like ZIO. There is overlap because ZIO gives you async today and LOOM gives you async tomorrow, right? So there's overlap between them. And I would say it like this: if the reason you're using ZIO is because you were sort of grudgingly dragged to ZIO because you wanted a better, faster future, then yeah, LOOM is going to liberate you from the constraint of an effect system. On the other hand, if you're using any sort of concurrency whatsoever, implicitly or explicitly, or typed errors or context propagation, interruption, precise interruption, back pressured interruption, all these different features, resiliency, then LOOM's not going to fix any of that for you, and you're still going to have, I think, a great place in your application for a library like ZIO. And this looks a little misleading here because it looks like, well, ZIO has all the checks, right? And LOOM doesn't. It's not exactly true. Because LOOM is bringing something to the table that ZIO doesn't have. LOOM gives us cost-free async. Well, not literally cost-free, but as cost-free as you could possibly hope out of a runtime system, out of a language. And ZIO is stuck in a world where async operations, of which there are numerous, have significant cost associated with them. In fact, async operations have cost in all effect systems, but due to the way that ZIO 2 is designed, they have extra cost in ZIO 2. Okay, because what ZIO does is it tries to execute your program on the JVM stack. If that fails, because, for example, it's going to need to trampoline, and it has to trampoline every time it hits an async operation, then it has to gradually unwind the JVM stack and save all of that information on the JVM stack onto the JVM heap. So it's transferring information out of the stack into the heap. And that's not free. The opposite of free is very expensive to do that. So you don't want your program to do that. So async operations are not cheap in ZIO, and they're as close as you can possibly want to free in LOOM. I've always thought that LOOM is the right way to solve the async problem. I think like the two-colored functions that Kotlin introduces, no, we don't want that. Ultimately, when we're using a high-level programming language, we want to be able to create as many threads as we want, right? And if it's too slow to make those operating system level threads, let's just make them green threads. Encapsulate that concern in the language itself. And every function should be async. Yeah, every function should not block an operating system thread. That's the way it's done in Haskell, right? That's a normal, sort of modern, reasonable approach to multi-threading. Create as many threads as you want, and the runtime will make everything scale. That allows us to program using the thread model, which is what we want to do, because it is no fun to program using the reactive model, message passing, all that stuff. That's a pain. We want a threaded model of computation, but we want to be able to create as many threads as we want, and LOOM solves that. So I've always been a big fan of how Loom is solving the async problem. And I want ZIO 2 to get along with Loom very well, to benefit from Loom. In fact, I want the performance of ZIO 2 to be higher on Loom than it is without Loom. And thinking about this, the heart of the issue behind the big difference between ZIO 2's async performance and Loom's async performance is this operation called async. And async, what async does there, you can see it right here. You can see this async operation here is async allows you to turn a callback-based API into a nice ZIO effect that hides the callbacks. So everyone using ZIO, whether you're doing sleeps or awaiting promises or pulling stuff from queue, you're all programming 100% async, even if it doesn't look like it. Right? The code you write in ZIO, it looks like it's blocking and is waiting stuff, and it is blocking, but it's sort of async blocking, not synchronous blocking. So it's not blocking operating system threads, it's blocking fibers. And so it can all be high performance and efficient, and you can program using the model that you want, even though behind the scenes, ultimately all async programming is programming with callbacks. And so you need an operation that allows you to take a callback-based API, because at the bottom, even though most of you have probably never, if you've only done work in Scala, you probably never saw a callback-based API, because it's all hidden from you. We have so many libraries to hide these things. But ultimately, async programming, if you look into the guts of Future or ZIO or anywhere else, or all the Future and ZIO wrappers on everything, even Java wrappers, it's all programming based on callbacks. So there's always a callback-based API in any async model of computation, unless you bake it into the JVM, which is what Java Oracle has done. And you need an operation to get rid of the nasty callbacks, so we can program using that nice sort of sequential model that we want of a thread executing one thing and then continuing on to the next thing without having to think about callbacks. And there's a lot of different kinds of overhead that go into this ZIO.async operation. The type signature looks like that. It's really, really hard to decipher because it's actually a function that takes a function, and the outer function just registers a callback, and then the inner function is the callback. And given such a sort of register function, ZIO can bundle that up into a ZIO effect. And the performance cost of this comes primarily from the fact that every time the runtime system encounters one of these ZIO.async types, it's got to suspend the fiber. And that involves putting it to sleep. And in ZIO 2's case, it involves saving all of the stack to the heap. And then the fiber's sleeping, and then someone somewhere will later call that callback. And they'll say, here's your value. That's the essence of async programming, is callbacks. So they say, here's your value. And then that value has to go into the suspended fiber, and the fiber has to say, oh, the next value is ready for me. I can continue my computation. And so it resumes, but when it resumes, in order to resume, it has to be submitted to some sort of thread pool or some sort of thread scheduler. And the scheduler has to say, okay, now I'm going to go ahead and run this. And that process actually is very slow. This is the reason why Future is so slow in Scala, because it actually suspends and resumes on every single operation. So if you call .map or .flatmap or whatever, it's constantly suspending and resuming. That's why Future is 50 or 100 times slower than the effect systems. That's a very slow operation. In addition, these async operations, they force you to trampoline. You've got to store all of that stack on the heap, and that's not a fast operation, especially when you have to do that in Scala. If you're doing it at the level of the Java virtual machine, that's one thing, because it's a mem copy. But if you're doing it at the level of Scala, it doesn't look like a mem copy. And it's not a contiguous, just sort of byte transfer. It's actually much more complicated than that. And then there's lots of allocations and also indirection, basically dynamic dispatch involved with this async machinery. So it's slow. It is slow. And if we're thinking about how we can tackle this issue, get to the heart of this issue, deal with this async performance overhead problem, we also need to talk about all of the other ways in which we would like an effects system to integrate well with Loom. And they are, I mean, I've put them in this table here just so you can see what it would look like to have no support of Loom, which is where all effect systems are today. They're right there. None of the effect systems supports Loom. Low support would involve so-called virtual thread support, which means mapping one-to-one. Every fiber should map one-to-one to a virtual thread. That bare minimum right there. Also, all effect systems have interruption models, and it's difficult to imagine supporting a Loom in any way unless you can somehow map between these two different interruption models. The Java has its own interruption model, and effect systems have their interruption model, and they're not the same. They're not even close to the same. But you want interruptions in the thread world to be seen as interruptions in the fiber world. And you want interrupting a fiber to interrupt the virtual thread that's executing that fiber's workload. So you want bidirectional interop here. And that would be, I would characterize that as useful support, like bare minimum, bare bones support. In the moderate support category, you would add two more things there. You would basically look for all the cases where you're using callbacks in the effect system, and you would try to delete those. Because remember, callbacks have overhead, and they lead to this very complicated high overhead process of suspending and resuming and trampolining and allocating and virtual invocations that slow stuff down. So you would want to eliminate that wherever possible. And basically have synchronous primitives, synchronous in the sense that they actually do block a virtual thread. Blocking virtual threads is cheap. And then also you would want to figure out how you can tie together these worlds where we have fiber stack traces and fiber dumps, and then over here we have thread stack traces and thread dumps. We need to tie that together in some fashion. If you look at a thread dump in Loom, you should see something different. Or you should see something that's recognizable to you if you do a fiber dump in ZIO, right? And same way around. And then high support would add to that the ability to not use ZIO.async, right? Not use that at all. So, or rather, not use trampolining, of which ZIO async is the chief offender, but there's other ways that, or there's other reasons you need to trampoline as well, but basically avoid trampolining whenever possible, because that's the way to squeeze the most performance from Loom. So let me run through these real briefly just so you can see what they look like. This is some ZIO code. How many fibers are running on between lines 3 and 4? Does anyone have a guess? So right after right and right before left result, how many fibers are running? 3? Yes. So that's exactly how many virtual threads we want and expect to be running in an effect system that's powered by Loom. We want one-to-one correspondence to the maximum extent possible. Every single fiber needs to be executed by a single lifetime virtual thread. Not changing virtual threads, but a single lifetime virtual thread. Also, you should be able to, from the ZIO world, you should be able to interrupt a operation like thread sleep. Okay, so thread sleep is a synchronous operation, and it does not know anything about an effect systems interruption model. So you have to find a way to translate the second line in that for comprehension is ZIO interruption. So ZIO interruption needs to translate into interruption in the Java thread model. And that needs to work in a lossless fashion. You see, you need to be able to preserve maximal information on, for example, who did the interruption. And that also needs to respect ZIO's ability to create sort of masking regions where it's not interruptible. For resource safety, you need the ability to say, nothing should be interrupted in here. This needs to happen atomically. You do that using a pair of operators in ZIO, and you need to have this integration with virtual threads respect those guarantees. Also, you need an interruption, like if a Java thread interrupts a virtual thread that's running a fiber, you need that to be seen from the outside world as an interruption. But that's already possible. You may not know that, but that's already been baked into ZIO, and I think Cat's Effect supports that as well. They support translating from interrupted exception into a fiber-based model of interruption. Basically, all of the cases where, well, first off, how many people in this room have used ZIO.async? 10? Maybe 10 people. How many people have used a promise or a queue or ZIO sleep or anything like that? All right, so trick question, all of you have used ZIO async. Even if you don't think you've used ZIO async, you have used it. And that's because all of the wonderful non-blocking stuff in ZIO is powered by ZIO async. Even something as fundamental as a promise or ZIO's queue and whatnot, 100% powered by ZIO async. So something like this, it should not use ZIO async underneath the covers. Promises shouldn't use async. Fork and join shouldn't use async. Basically, ZIO should never use async. Async just can make you slower. Why use it in a world with virtual threads? You should be able to create ZIO code like this that blocks for a really long time and be able to immediately get a stack trace, a useful stack trace from that without any delay. You should also, if you go into and use JCMD to do a virtual thread dump, you should be able to see your ZIO fibers in there. And they should have the same names that you see over in the world of ZIO, right? The tooling, we were in a world where the ZIO tooling was quite different than the JVM tooling. But we're coming into a world where we can start to see some unification, where over in the JVM world, you can actually see your ZIO fibers running and they have the same names. That's really cool. This is what you want. In addition, and this is sort of in the high support category, code should avoid the trampoline wherever possible. So you should be able to do some very complicated code like this. This code here, it iterates over, first off, it uses some interruptibility stuff, so it doesn't permit interruption anywhere except when you're doing the work on an individual open file. But it iterates over a bunch of files, opens them, does some work on each file, and then closes them for each file. And then it collects all of the results of that work. So this code here, it should execute 100% on the JVM stack without any trampolining whatsoever. Why? Because it'll be faster that way. There's no need. Despite all the async stuff that's happening in here, when you're relying on virtual threads, you don't need that ZIO async operation to have the high performance that you would expect. So that's a lot, right? That's a lot of work to do. Where are we today? Well, I'm happy to say that we're almost there. We're like a few days of work away from having 100% of these boxes checked in every category. So another reason to look forward to ZIO 2.1. And no breaking changes, by the way. I don't know if Adam said that, but 100% binary and source compatible with ZIO 2.0. What does this mean for you? Well, I think we're still learning and iterating and polishing and creating more benchmarks to understand what the impact of Loom will be on your application. But I can share with you an interesting preliminary benchmark that sort of blows me away. And what I did here is I created a little concurrent harness consisting of one server and 100 clients. And the server is multi-threaded, or multi-fibered, as it were. And then obviously every client is running on its own fiber. And every client connects to the server and tries to read a megabyte worth of data from the server. And that's done by reading 1,000 chunks, each of which is a kilobyte in size. So that's the chunk size. Not unrealistic measures for a benchmark in this nature. And I coded this up in two ways. One using the async operators that are built into CATS Effect 3 and ZIO 2. And you get the numbers you see there, so around the same 2.7, 2.8 operations per second, where every operation is 100 clients all reading each 1 megabyte, so 100 megabytes in total from a server. So you can do that roughly 3 times in a second. And then when you do that without an async node, without all of the non-blocking I/O stuff that you've probably grown to hate from the Java NIO2 package, right? It's not fun stuff to use, but it is best practice, the way you should be building your non-blocking clients and servers. When you code it using straight up dumb input stream that has existed since the earliest days of Java, you get performance that's more than 4 times faster. This is an I/O benchmark. And the fact that we're getting performance that's 4 times previously, you know, state of the art using NIO and an effect system, all non-blocking code, is pretty impressive. Obviously, we're going to be doing other benchmarks in order to establish a sort of round picture. This is not a round picture, this is a single benchmark, but it is not surprising to me that deleting all of that overhead that is implied by every async can end up improving performance by a significant margin. And actually, it's more than 4 times faster because it was going so fast that I was basically having OS level resource errors. So I had to insert retry logic to get the benchmark to complete. And the retry logic slows it down because it has to retry occasionally sporadically in the benchmark. So it introduces a lot of jitter. But it is interesting that I'm seeing these type of numbers. So how about some recommendations I can give to you that will help you better prepare your applications for a post-Loom world. I actually think Loom is going to be the reason why companies decide to upgrade to a more recent JDK. Because there's nothing super compelling in all the intermediate one. A lot of people are still on 9 or 8, right? But Loom 19 was when it shipped, and it's in 20 as well. You have to enable a preview mode in order to get all the bells and whistles. But it is very compelling stuff. And the fact that it can take all your legacy code and make it best practice is amazing. And obviously you've seen here, and you're going to see more benchmarks that are going to show you that if you embrace Loom, if you support it in the effect system, you can achieve significant increases in performance, even of straight up I/O stuff, which formerly used to be the sweet spot for these async effect systems. Non-blocking I/O was a sweet spot for them. So number 1 recommendation, well, use ZIO 2, right? Because just like if you use ZIO 2, I used ZIO like 2 years ago, you didn't have to worry about callbacks. You could have synchronous code and async code, and from ZIO's perspective, it looks the same. So that was a big reason back in the day to use effect systems, is that you can unify across sync and async code. You only need one model of computation. And now in this world where, okay, now you have a new type of legacy code. It's all the async code that you wrote over the past decade. All that's legacy. And now we need to go to a different world. Well, if you just use ZIO 2, basically you don't have to change anything. And suddenly things will just be getting faster when you run ZIO on a JDK that supports Loom. This is not even a separate build of ZIO. Okay, this is transparent support that kicks in when it detects Loom. And it's just enabled, and your code starts behaving differently because it's working in a different way. Avoid using ZIO async. And it should not be surprising why I'm telling you to do that. But any use of this operator is going to slow you down, and you will be able to measure that in benchmarks. Stay away from this. And that means not just direct use, because almost none of you have ever used this operator, which doesn't surprise me, but indirect use. So if you use a library that's using async, that's still could be in the hot path, could be negatively affecting your performance. So stay away from async. And we're going to be in this intermediate period where we have to support the async way of doing things as well as the new Loom way of doing things. And so ZIO 2.1 is shipping with this operator called green thread or else. And green thread or else lets you specify one effect that will be run if you are running on a platform that supports green threads, which right now today is Loom. But it could be at some point in the future, Scala native has green threads in which you would do that first thing, if you wanted to do something differently. So that's where you put your blocking code. Your thread sleep or whatever goes in that block. And then over on the other hand side, the second argument is the effect that you want to execute if you are not running on a green thread. And so that's where you put your ZIO async. So using this simple pattern, you can support Loom code bases and non-Loom platforms at the same time with a unified code base. So I encourage you, all of you ZIO library authors who are watching either here in person or remotely, think about this. Go through your ZIO library and look for all ZIO async and replace it with this pattern. This will allow you to support both worlds simultaneously. Another recommendation, avoid TYPELEVEL. And that's because, TYPELEVEL has lots of great libraries. Obviously, people are using Doobie and HTTP4S, but we're entering a fork in the road here where the TYPELEVEL libraries are designed for a world where async is the workhorse of async computation. So they're going to freely, just without bound, use async, right? Just use it here and there, use it everywhere. Use of async is rampant and will continue to be, for the foreseeable future in that ecosystem. So this is a reason to preferentially shift in cases where there are alternatives to ZIO-based libraries, because we're going to be strongly encouraging ZIO people or ZIO library authors to simultaneously support the Loom world as well as the non-Loom world by using that green thread or else operator. So that's going to give you maximum performance and also a smooth upgrade path. And then, at some point, Cat's Effect 3 might take a similar path. And in that world, they might update their libraries so they also support the dual path. But until then, basically, if you're using, for example, all ZIO except for HTTP4S, well, that might be a problem because HTTP4S is going to throw in a bunch of async nodes. So you're not going to achieve your super fast, Loom web server by using HTTP4S and ZIO because you need to avoid that trampoline, you need to avoid the async node, you need to let the virtual threads do the heavy lifting if you want to see significant performance increases. Also, consider increasing your stack size. So in Loom, or even in ZIO today, you have a smaller number of threads doing the work for a large number of fibers. So if you only have a few threads, it's fine to give each one of them quite a significant stack size. And one thing I will be implementing in ZIO is the ability to look at the stack size and make a decision on how long it's going to keep trying to execute something on the JVM stack. Right now it has hard-coded parameters that work for the majority of users, but it's relatively small change to go in there and say, if you give ZIO, or if you give each thread more stack space, then I'm going to let you run longer and longer and longer on the JVM stack before deciding you have to trampoline. That's going to help you, give you an easy knob that you can turn in order to stay away from the trampoline for longer and longer periods of time. All right, so that's where we are today. We are on the verge, a few days or maybe a couple weeks at most from ZIO 2.1. We'll ship the first RC probably very soon that has the streaming work in there, and then we'll ship another RC with the Loom support. And what's next from my perspective is finish this PR. You can take a look at it and the benchmark and see all the stuff that I've talked about tonight and see how the integration works between Loom virtual threads, and also see how it's supported in a transparent fashion. There's no work for you to do in order to benefit from this. And then we've got to, after this gets merged in, we've got to roll out ecosystem support for Loom. And this means obviously updating ZIO organization libraries to have dual support, but it also means working with third-party libraries, like obviously Pierre's here, and there's the excellent Caliban and Shardcake, and then there's Backtask, which we saw, and Elasticsearch, and so many other great third-party ecosystem libraries out there. We've got to work with the authors of these libraries to support both of these modes. Because a ZIO developer, you want to be able to upgrade your JDK to 19 or 20, and then instantly things just become faster and better. And to do that, we need to get the whole ecosystem on board with Loom. So that's something we're going to be pushing for. And I'll personally upgrade the runtime system to what I'm calling Gen 3++, which I'll talk about in a second. And then there's lots of room for improvement here. Remember, the ZIO runtime system is very, very new. It's 10 months. Okay, so you should expect there's a lot of low-hanging fruit that we haven't even picked up yet on performance. And in particular, the Loom support is going to be brand new as of 2.1. So it means there's lots of new ways, like we could think about doing a custom like Loom-aware scheduler at some point. Who knows, different directions we can take this, but there's a lot of room at the bottom to make this thing way faster than it will be even out of the box, and it's going to be pretty fast out of the box from what I've seen. And then the other thing in the ecosystem we'll have to think about is, like we have a ZIO Neo, which is an NIO-based library, and that doesn't really make sense anymore, right? So maybe that library needs to be refactored to be ZIO IO, and it provides a sort of Neo, an API that either works on blocking IO, sort of Loom IO, or one that works on non-blocking IO, depending on which JVM you're running. Right now, it's a straight-up wrapper of NIO, and I don't think that makes a ton of sense, because that's committing you to the async way of doing things, which we know is not going to be as fast as the Loom way of doing things. So the Gen 3++, as I'm calling it, basically, remember right now that the ZIO 2 runtime system, it tries to execute effects on the JVM stack. And then it will later give up if it can't, and then it will trampoline. However, we already have so much metrics and metadata inside the runtime system that's being utilized for things like auto blocking. Like if we detect a fiber's blocking, we shift it onto a separate thread pool that's designed for blocking computations. And that it happens based on looking at data that's coming out of the runtime system. So we have enough data actually to say basically whether or not it makes sense to always trampoline or fallback trampoline. So the current runtime system has fallback trampolining. But let's say we know a particular effect uses a lot of ZIO async. Like maybe every other instruction is a ZIO async, right? So that thing's going to be trampolining all the time. For an effect like that that's composed mostly of ZIO async, that should be run in a trampoline mode, always. You should never even try to run that on the JVM stack. You should just always use a trampoline. That will be faster. So this optimization involves adding the ZIO 2 runtime system already has a fallback trampoline executor, but sort of pulling that out into its own thing and being able to dynamically decide, should this fiber execute using the fallback trampoline or using the always on trampoline. And that's a huge optimization, because we already know we're by far the fastest at asynchronous workloads. Like ZIO 2 is really fast at synchronous only workloads without any async. But the async has a cost. And ultimately, there's a few minor things we can do to pay down that cost, but I've already done most of them. There's not much more I can squeeze out of that. So the ultimate path to blazing fast performance in all types of effects is to be able to detect fibers which we know are going to perform better if we execute them always on the trampoline. So that's what I'm calling Gen 3++. It's not novel work here, it's more of the same, but I think will be a really, really nice addition that maybe we'll see in ZIO 2.2. So in summary, ZIO 2.1, even though it's 100% backward compatible and not introducing really any new features per se, I think is really upping the game, once again, with best-in-class Loom support. We're going to check all the boxes and make sure that that Loom integration is ready to go. And it's going to give you faster async performance without you having to change a single line of code. And ultimately, as we upgrade the ecosystem, you're going to see these changes percolate in these different libraries that do everything from web serving to GraphQL serving to this and that. All of that stuff is going to come for free. So just continue to use ZIO 2, continue to hopefully give us great feedback on how we can make this ecosystem better. And then encourage a small word of encouragement or appreciation for the contributors to the libraries that you use always goes a long way. We maintain most of these libraries in our spare time, you know, in many cases, and a lot of the libraries out there are not sponsored, right? They're just people like you and me who are writing libraries to solve pains that we have. So I personally greatly do appreciate all the new libraries that I've seen and the new modules I've seen just in the talks today. Thank you everyone for the work that you're doing contributing to the ZIO ecosystem. All right, so that's it. Thank you very much for attending my talk.